let's suppose that you have someone who's standing on the equator. And as you guys know, gravity always pulls you everywhere on the surface of a sphere towards the center of that sphere. So in this case, you would have a weight that's actually pulling you towards the center of the Earth, right? And of course, the surface responds with a normal force pushing back on you this way, okay? So the question is, do you feel less weight at the equator, right? Do you feel more of a sense of a weightlessness because N is going to be reduced because of centripetal force, all right? And the answer is yes, you do. And if the Earth were spinning fast enough, you would even experience feeling weightless, okay? So let's prove that. Let's prove that. In fact, let's find a velocity, what speed the Earth must be turning such that you would actually feel weightless. All right, so summation of forces in X must equal to mv squared over r, right? When we're talking about circular motion, this is our Newton's second law, okay? In this case, we have weight pointing towards the center of the Earth, right? And we have a normal force pointing in the negative x direction. So weight's pointing positive x direction, normal force is pointing the negative x direction. And in this case, the centripetal force, remember, always points towards the center. At this location, that's going to be in the positive x, so that's plus mv squared over r. So take a moment to think, what creates the sensation of being weightless, right? I'll give you guys a second. Remember from an earlier problem that the normal force going to zero is what creates that sensation of being weightless, right? If the floor is not really pushing back up on us anymore, we don't really feel like we have any kind of weight, right? So that goes to zero. And so really what we're asking is, when is the weight, right, equal to centripetal force, right? In other words, what velocity of the Earth spinning will create a sensation so that there's no more normal force, all right? Well, this is a beautiful thing. This is so satisfying when this happens, when I get to cross out my m's. So I'm crossing out my m's here, right? And so I get g is equal to mv squared over r, right? If I solve for v, I get v equals square root of, actually, this is gone, right? I get the square root of gr, right? Okay, so, well, what speed is that such that that happens? Well, I go ahead and put in my g, which is 9.8 meters per second squared, okay? And my r, in other words, my radius of the Earth, last time I checked, was about 6.4 times 10 to the 6 power meters, right? And if I put that in my calculator, press the button for enter, I get about 7,900 meters per second. Okay, I did a little bit of rounding there, but to a first approximation, it's about 7,900 meters per second. Okay, that's fast. That's really, really fast. Okay, and that's what would be required if a planet was going at that speed. We would have a sense of weightlessness. Well, if our specific planet with this specific gravity. Okay, so that begs another interesting question, which is part B for this slide, that says, how long would a day be if the Earth were spinning that fast? Okay, so in other words, again, this is a period question. We're trying to find the period here. Okay, and the thing is, we would just say that, I'm going to little box this off here, period equals 2 pi r over v, right? 2 pi r is the distance of one's spin, and velocity is the speed, right? And so, well, let me put in my values here. I have 2 times pi times the radius of the Earth, again, which is about 6.4 times 10 to the 6th, right? And I divide that by this guy that I got over here, which is 7,900 meters per second, right? For a grand total of how many seconds is that? Well, I get about 5,063 seconds, right? Just say approximately 5,000 seconds, which is approximately 1.4 hours. Okay? That's a very, very short day on Earth, okay? It would be, yeah, so it would essentially be turning each day into 1.5 hours, okay? Luckily, that's not the case. Although it would feel kind of neat to be nice and weightless if I was close to the equator. The interesting thing is this effect wouldn't happen for someone standing on the North or South Pole. They would continue to have their full normal experience of weight. Cool. So great for a dinner conversation. I hope you share this with everyone you know. Scott, signing off.